Hello, I'm Simon Gay, and this is video 1.3 of the Information Management section of CS1F. Let's start to talk about strategies for data management. Here's a simple idea. A program where all the data is just held in the program's memory, in variables, arrays, lists, whatever, but with no data persistence between different runs of the program. The data would be reconstructed or perhaps re-entered, pulled in from some external source at each invocation of the program, each time the program is run. This is clearly not what we want. If we're working with a large amount of data, it seems impractical to rebuild the data store every time we start the program. The second idea is to keep data in files on disk, which can be accessed by different applications. Each application would be responsible for putting its own interpretation, creating its own presentation of the data. But there are a number of problems with this idea. It might be difficult to coordinate between applications if different applications both want to update the data, for example, or different versions of the data could develop if one application wants to make a change and another application wants to stick with the original data. So there are problems here too. The third strategy is to combine together all the functions of data storage and access for a related set of tasks. And there are a number of examples here. And this is the strategy that we're going to follow. A system like this is what's known as a database management system. And when we say database, what we really mean is a database management system. So all of this organization and management of operations is implicit in the term database. We're talking about storing related data in a structured manner with as little redundancy as possible. Each piece of data should be stored in just one place, so it's known how to access it. The database should give all of the necessary users access to the data, and they can view it, they can add new data, they can update existing data, but within the limits of the access rights they have. So there may be different categories of users. Some users may only be able to view certain parts of the database, while other users may have the ability to enter new data or to modify data that is already there. And a final important point is that the database should be viewable and also writable, updatable by many users at the same time, using controlled concurrent access. And what we mean by controlled concurrent access is that if one user makes a change to the database, then this change should be seen by all of the other users. And the database should always be maintained in a consistent state. Now, the field of databases has evolved over the years, like all other areas of computing. And the list here is a chronological list of several different kinds of database. So the first idea, going back quite a long way, was hierarchical databases. And this is where data is stored in a tree-like structure, where each area may have further data descending from it in a parent-child relationship. And the filing system in your computer, what you look at in Windows Explorer, for example, you see folders within folders, you see files within folders. That is a hierarchical data store. A generalization of the hierarchical idea is what's called a network database, where you don't have this strict tree-like containment relationship, but you have a more general relationship of a network of nodes and links between them, through which data can be related to each other. And a characteristic of both hierarchical and network databases was that it was necessary to know the structure of the database in order to find any of the information. So you had to find information by following a path to it. And this is like needing to know which folder you've put one of your documents in on your computer filing system. And then we get to the idea of relational databases, which really became the standard. And relational databases were introduced in 1970 by Edgar Codd. And 1970 is a long time ago. We think of computer science as a very rapidly evolving, rapidly changing subject, and it is, but it does have some very secure foundations which go back quite a long way. And the theory of relational databases is one of those foundations. So the key innovation with relational databases was the idea that you should extract information by giving queries for what information you want without needing to know the details of where and how it is stored. So relational databases became very widespread and standard. And then sometime later, mainly in the 1990s, the idea of object-oriented databases arose. And this went hand in hand with the development and increasing popularity of object-oriented programming languages. So data in an object-oriented database is organized in a similar way to the concept of an object in a programming language. And object-oriented databases can be linked with programming languages to give a persistent store that can be used by a program where the data persists from one run to the next. And finally, the most recent development is what are often called NoSQL databases or NoSQL databases. And you can interpret the NoSQL part as either meaning no SQL, so they're a completely different structure. You don't query them using structured query language. They're not based on relations. Or you could interpret the NO as standing for not only SQL, meaning that SQL queries are possible, but it's also possible to access the data in other ways. And these kind of databases abandon or generalize or go beyond the relational database model for reasons such as working better in distributed systems, being able to store redundant copies of data on a number of different computers. We started off saying that redundancy is bad, but sometimes redundancy is good if you want fault tolerance, for example. If one of your computers breaks, then it's a bad thing if that's the only place where certain data was stored. So here are some examples of particular database systems in each of these styles. And if you're interested, you can look up some of those. Especially you might be interested in looking up the more recent NoSQL style of databases. But we're going to concentrate on relational databases because understanding these is really a good foundation for everything we might want to do in the world of data. So here's an example of a relational database. And we think of a series of tables where each table collects together related information. So here's a greatly simplified example that you might find in a database of a bookstore, such as Amazon. Here we've got a table called products, and this table has a schema which consists of these column headings. So these are descriptions of the data that's going to be stored. We have a product ID, a product title, in this case the title of a book, and then a more extensive description of the book. We've got the ISBN, well, that only applies to books, so we're really talking about books here. We've got a supplier, which is identified by a code number here, and this is the number of copies of this book in stock. So that's the schema. And then within the table, we've got the data itself, and each item of data is a row where there's a component of data for each column in the schema. And then if you've got 10,000 books, there would be 10,000 rows in this table, each of them following exactly the same structure, but of course having different details corresponding to each specific book. And then there can be other tables to store other information that's relevant in the database. So here we might have a table called customers, and each customer has an ID number and an email address, and maybe other pieces of data as well. And we're interested in suppliers. So here's a table of suppliers where each supplier has an ID and an address and maybe other information as well. And then these tables can be linked together. So the point here is that supplier 2847, that's the supplier of Database Systems, the complete book. And if we want to know any more about that supplier, we have to go to the supplier table and find data that's associated with supplier ID 2847, and then we can see the address. So what operations can we do once we've got this database? Well, we can construct views, we can look at the data that's already in there, and we can manipulate the database. So we can add new data, or we can change or update existing data. So just think for a moment about some examples of views and manipulations that we might want to support in this book database. Pause now. And now we're back. So one example of a view would be to show the details of a particular book, to see its description, see its ISBN, and see how many we've got in stock. Another example of a view could be to see all the books that a particular customer has ever bought. An example of a manipulation could be to change the number of copies that we have in stock of a particular book if a book is sold. Or maybe one of the suppliers moves to a different address and we need to manipulate the database by updating the address of that supplier. Here's another question for you to think about. In how many places in our database do we have the address of the supplier of the database systems book? Pause and think about that. And the answer is in just one place, because every time we refer to the supplier, we use this ID number, this 2847, and the address of supplier 2847 is stored only in the suppliers table. So we don't have redundancy. We don't have the possibility of different copies of the same information becoming out of step with each other. And as we said before, the database system will support all of these view and manipulation operations being done concurrently or simultaneously by many different users. And coming back again to this idea that databases avoid redundancy, we want to avoid ambiguity, and we want to avoid inconsistency. So let's illustrate that with an example. So Dilbert here has worked hard and produced a database with some geographical data. And here we see a table which is about towns in England. We've got the name of the town, we've got the county that it's located in, we've got the population of the town, we've got an indication of whether or not the town is the county town, the headquarters of its county, and we have an indication of whether or not that town has a cathedral. So that's quite clear. And along comes pointy-haired boss and says, I want the county population details too. And by the way, I'm interested in Essex, which doesn't seem to be in your database. Okay, so what is Dilbert to do? Think about this. Suppose we just add county information to this table in whatever simple way we might think of. What are going to be the problems with that? Pause for a moment and think about it. Now we're back. Let's see what we might mean by adding county information. Here we are. The table is a little bit bigger. We've added an item, two items actually. We've added county population and we've added county size. And notice here that because the county of Hertfordshire occurs 3 times, because we have 3 towns from Hertfordshire in the table, the population of Hertfordshire has been entered 3 times. And also the size of the county, 631 in whatever units that is, has been entered 3 times. And the boss said he wanted Essex in the table as well. So here is Essex. It's just sitting there by itself. It's only as a county. There's no town associated with it, so there's no town population. There's no information about a cathedral. But here we've got the population of the whole of Essex and also its size. So what's the problem with this? Well, One problem is that we have redundancy. We have the population of Hertfordshire stored in 3 different places, and if we need to update it, we need to find all the places that it's stored and update the population. So to update the population of Hertfordshire, we need to know every town in Hertfordshire that's in our table, and we need to go and change this number for each of those towns. And that seems a bit complicated. There could be a possibility of missing one of them out and ending up with different population numbers for different occurrences of Hertfordshire, and that would be a bad thing. That would be inconsistent. And there seems to be something else unsatisfactory about this new table. We've got some information about the population of Essex as a whole, but we don't have any information about individual towns in Essex. So Essex is not being treated in the same way as all the other counties. And this is a problem of not having every row in the table following the scheme of the table. Not all of the columns are filled in for the row that contains the county of Essex. So we try to avoid this redundancy. We try to avoid the possibility of inconsistency. And there's another little example here. If we imagine we've got a system where there are concepts of billing, customers, accounts, and phone lines, we may have different groups of users who need to access different parts of the whole data. So the billing team is interested in billing and customers. The technical team is interested in accounts and phone lines, but doesn't need to know about billing. And everyone is interested in customers and accounts. But we only want one record of customers, which is accessible by all the users who need it. We only want one record of accounts, which is accessible by all the users that need it. If we want to change information about a particular customer, we want to do that in just one place so that the change becomes visible to everyone who's going to use that data. And what we'll find when we start building our databases is that we want to avoid having data repeated in different places. That would be a poor design. And so part of the design process for a relational database is making sure that we know exactly where is the one place that each item of data is going to be stored in. So we will not do things like produce a single table with both towns and counties where there's missing data in some of the rows. Now we've talked about this idea of controlled concurrent access, so I want to explain exactly why a database management system needs to be careful about that. So a database can have many users reading and writing at the same time. This diagram illustrates the idea for, you could think of this as a database accessible over the internet. You've got a server directly mediating access to the database, but a number of clients who are going to connect in and ask for data or try to update it. And we need to make sure that each user sees a correct and consistent view of the data. And in particular, we need to make sure that allowing concurrent access doesn't cause any incorrect updates leading to inconsistency of the data. So let's look at a specific example of this, which is a bank account. A bank has a database of accounts, and here we've got a table where we have customers and we have the bank balance. So Mr. and Mrs. Bloggs have a joint bank account, and the balance at the moment is £100. One of the operations this database supports is withdrawing cash. So Mr. or Mrs. Bloggs can go to a cash machine, an ATM, and they can ask to withdraw a certain amount of money. And to illustrate this, we've got a little bit of code here, and this is supposed to be code that's sitting inside the cash machine. So what does the cash machine have to do if the person standing in front of it asks to withdraw £10? Well, the code inside the cash machine has to get the current balance in the account, it has to subtract 10, and then it has to do an operation that we've called set balance to update the amount of money in the bank. I hope that's clear. Now let's think about what happens if Mr. and Mrs. Bloggs each decide to go to a cash machine. They go to two separate cash machines. They both decide to withdraw £10 at exactly the same time. Pause for a moment and make sure you know what the final balance in the account should be. Of course, we want it to be £80. 100 minus 10 minus 10. Let's see what can go wrong. Here's Mr. Bloggs at his cash machine. Here's Mrs. Bloggs at her cash machine. Mr. Bloggs' cash machine asks for the current balance and gets the answer £100. Mrs. Bloggs' cash machine asks for the current balance and gets the answer £100. So far, everything is correct. Mr. Bloggs' cash machine withdraws £10, gives Mr. Bloggs a £10 note, and it updates the bank balance to 100 minus 10, which is 90. And there we are, balance of 90 sitting in the bank's database. But the cash machine that Mrs. Bloggs is using hasn't finished yet. It also gives Mrs. Bloggs a £10 note, subtracts £10 from the balance it had, which was 100, and updates the balance again to 90. And this is a problem because Mr. Bloggs and Mrs. Bloggs have each been given a £10 note, but their bank balance is now 90 instead of 80 as it should be. So pause for a moment and think about other examples in real life where the same kind of thing could happen and where it would also be a problem. I'll give you two examples. One example is an airline booking system. Imagine that Mr. Bloggs and Mrs. Bloggs are both trying to book tickets on a flight from Glasgow to London, let's say. There's one seat left on the flight, and it would be a problem if Mr. Bloggs and Mrs. Bloggs both get given a booking for that seat. A similar example that might be of interest to you is when you're signing up for your university courses on my campus. If there's one place left in a particular CS1F tutorial group, then it would be a problem if two students try to book into that place simultaneously and both think they've been given a place in that tutorial group. So what's the solution to this kind of problem? The answer is the concept of a transaction. So a database system that uses controlled concurrent access is based on transactions. And a transaction is one interaction with the database which is complete in itself. And the system makes sure that only one transaction is happening at a time. And this is achieved by locking the database when a transaction starts. So coming back to the cash withdrawal example, when Mr. Bloggs starts asking to withdraw £10, the database containing his account information is locked from the point where his cash machine gets the balance to the point where the cash machine updates the balance to 90. And being locked means that during that period, the other cash machine is not allowed to do anything with the database. It has to wait. Which means that when the cash machine that Mrs. Bloggs is using starts interacting with the database, the balance has already been updated to the £90 after the first withdrawal. Then the second withdrawal goes ahead and the final balance will be £80, which is correct. And it doesn't really matter which cash machine gets in first. It doesn't matter whether Mr. Bloggs does the withdrawal first or whether Mrs. Bloggs does the withdrawal first. The end result will be the same, that the bank account has the correct balance of 80. If we think about the airline booking system with two customers both trying to book the last seat on a flight from Glasgow to London, it does matter which one of them gets in first from the point of view that one of them is going to get the booking and the other one is going to be disappointed. But all the airline really cares about is that the seat is sold just once and not twice. So that's how transactions work. So, summarising, we're talking about database management systems. Often we'll just refer to them as databases, and These are 4 key points that we've covered, which the database management system needs to ensure. And in the next lecture, the next set of 3 videos, we'll say more about these points. Now, onto something slightly different. There is a recommended textbook for this course, Database Systems, the complete book. Here are the details. It's recommended rather than required or essential, so you don't have to buy the book. But if you do want to buy a book to go with the course, this would be a good one to get. It's very large, very detailed, very comprehensive. It goes far beyond this course, and it would be a good reference for any future work on databases during the degree. The book is in the library. There are some physical copies in the library, and it's also available through the library as an ebook, so you can check it out and read it. I will also mention that if you Google for the title of this book, it is possible to find complete PDFs of it on the web. And at various points during the lectures, during the videos, and on Moodle, you will see recommendations for sections of the book to read, and also recommendations and links to other reading material, sometimes in other books, sometimes on websites. And here is the recommended reading for the first lecture, videos 1.1, 1.2, and 1.3, and also looking ahead, some recommended reading for the second lecture, that is videos 2.1, 2.2, and 2.3. And this is the end of video 1.3. I will see you next time when we start on video 2.1.